Okay, um, now that we know what structural and behavior descriptions are, let's take some good examples. So let's go back to our mux. Again, this is a mux, inputs, two inputs, one select signal, one output, nothing much. This is the description of our mux, and just a quick reminder, the description is as simple as having an if statement. If the select is 0, I would want the output to be the same as input 0. Otherwise, if the select is 1, I would like to have the output as the same as input 1. Now, what is this? This is called the sensitivity list, and it's basically the trigger at which you would expect this hardware to function. The trigger at which you would expect your circuit to actually do the behavior. And for combinational circuits, you usually want this to be all the inputs. Okay, think about it this way. If we have, for example, oops, bear with me. This is my first time using a drawing tablet thing, so it's a bit annoying for first-time users. This is a combination circuit. It has inputs A, B, C, D, and the output O. I like imagination in naming. Anyway, when do you expect this circuit to execute, to change the output? Whenever any of those inputs change, doesn't matter which. If any of them changes value, you would expect to see a change on output, right? That is what a combinational circuit is. So in a combinational circuit, you expect the hardware to always function, not on a certain condition. You expect it to always function. And by saying not at a certain condition, it means when any change happens, which means you basically have to specify all your inputs in the sensitivity list. Okay? You could be tempted to say, but I feel like this is a mux, then we should only have the select in here. And let's really discuss what this would look like. Let's say, for example, that I have this description with only the select signal in the sensitivity list. So basically, I am telling the synthesis tool to do this behavior, which is the behavior of the mux, but I'm telling it to do it only when the select changes. How would the synthesis tool understand this? Okay, let's actually understand it ourselves and then describe what the what Quartus would do. So you have, oops, you have a nice mux here. Select signal. You have inputs A and input B, and you have your output O. And you're saying I want the behavior of the mux to happen only when the select changes. So let's assume that select is initially at 0, which means the output right now, I'm just going to call it out, so it will be distinguishable from 0. Output right now is equal to A. And let's say that A is also initially 0, which means output is equal to A is equal to 0. Okay? Now, what happens if I move select from 0 to 1? You would expect the behavior of the mux to actually happen, which means the output will be equal to B, which I will assume is also initially equal to 0. Okay? Okay, so select is now 1. The output is now, forget this, the output is now B and is 0. Now, what happens if B changes from 0 to 1? Select is the same. It has not changed. So the trigger that you told Quartus about, which is select, the trigger has not changed. What do? Well, Quartus understands that if the trigger does not change, then the output does not change, then it wants to keep this output as 0, even if this guy comes up at 1. And what this means is it will introduce some memory elements. It will introduce sequential elements, which is a latch, and it will no longer be a combinational circuit. So it will introduce a latch after here, which will basically hold the value of the mux until the select changes again. That is not what we want. So for combinational circuits, you have to have all the inputs in the sensitivity list. That is a must. If you're not listing all of them here, you will end up with some sequential elements, and the circuit will not be what you expect. If you have a pretty complex behavior description, and then you have a long list of signals that you will have to list in here, luckily there is a shortcut for you, which is saying if anything changes. This asterisk means anything. So if anything changes, this always statement will happen. And that is sort of the default for describing combinational circuits in an always statement. And I will pause the video to get my charger, and then I will come back. Okay. Well, now that I have my charger, let's go on. So as we said, you can just use this asterisk if you don't want to list the entire signals list of signals by hand. Okay, another note about this if statement. Some of you may be tempted to think that this else is redundant. Let's remove it. But now if you think about it this way, let's understand what the behavior is going to be in this case, which is saying if the select is 0, I want the output to reflect any change in the input 0. And that's it. No other changes. This is effectively a latch. It's a sequential elements. Okay. So always be complete about your behavioral description, and always pay attention to what you should put here. Any mistakes in the behavior will introduce you to hardware that you did not intend. Okay, you can always verify that, of course, by using model sim. Now, a third note: any signal that is written to in an always statement must be defined as a reg. So output reg. If it was originally a wire, say wire X, then instead of a wire, it has to be reg X. If it's an output, it has to be output reg X. Anyway, a reg is not to be confused. It is short for a register, but unfortunately that's a misnomer. That is not what it's actually intended for. Anything that is written to in an always statement, even if it's combinational, must be defined as either reg if it's internal, or if it's external, output reg. That doesn't mean it's the register, okay? So not to be confused with registers. It's just a name. A bad one, but it's just a name. Now, just showing you with another way to do muxing. It's exactly the same way. The sensitivity list here is the short form notation instead of the entire list of signals. And instead of an if statement here, we decided to use a case statement, and also I did not put the reg. So it's just showing you a different way to describe the behavior, but it's going to be exactly the same. This is the case statement. If the case is that select is 0, then the output is input 0. Oops, this is input 1, not 3. And then otherwise, the output is input 1. And just the same way that you were not supposed to get rid of this else, this default is also here to stay. It is not redundant. If you remove it, you will end up with hardware that is not what you expect. Now, those two examples are pretty simple, but to show you that they can do more, let's look at some complex form of muxing. This might be useful for part 3 of the lab. In this case, when the select is 0, consider this a 4 input mux, but instead of just describing what input to use, I'm also putting a hardware operation happening here. So I am saying, for example, when the select is 0, 0, I want the output to be input 1 and input 2 ANDed. When it's 0, 1, I want the output to be input 1 and input 2 ORed. And then when the select is 2, I want them to be XORed. When the select is 3, I want them to be this signal, and this signal is an addition. And again, we should put rig here. Oops, sorry. Okay. This basically, if you're confused about how this will be synthesized, let's go back and row again. Okay, so to describe this complex signal, let's first say that we have 2 inputs. Each input is 8 bits. We have a select that is 2 bits, which means it will be a select it will be selecting one of 4 things, and then the output is also 8 bits. This is the structure for mux. We have a case statement. We have a different value for the outputs at every stage. But instead of defining a simple signal as the output, we also put some complex description here. Let's see how this is going to be synthesized. Again, remember that the inputs and outputs are 8 bits each, but the select is 2 bits. So this is going to be described as something like this. Synthesized as something like this. You have a nice mux here. 4 inputs. Bad drawing. 2 select signals. So this is select 1, 2, 0. This is the output. And in the first case, you're going to end up with an AND gate taking input 0 and input 1. In here, it's going to be an OR gate doing the same. And so on. And actually, assuming this is 1 bit, only 1 bit, this is only 1 bit, 1 bit, 1 bit, this is also 1 bit, you take this entire thing, well, the CAD tool will take this entire thing and it will replicate it 8 times for each of your 8 bits. That is how this is going to be synthesized. This could be particularly useful for your part 3 of the lab, because in part 3 of the lab you'll have to build your ALU, which will be some complex things that you're going to mux out to your output. The next video will have some other examples as decoders, and then we will describe sequential elements after that.